defined on, say 0 to infinity, and if an is a sequence such that I probably should use a different word. Replace an if by suppose. Suppose f is a function defined on this, and an is a sequence such that a sub n is equal to f of n. Okay? What does that mean? That means that you start up, you have an, which you plotted is something like this, for example, right? And then at the same time, you also have f, which is a function from 0 to infinity into r. And therefore, you can graph it as a curve. Is that right? And that curve happens to contain all the points. That's what I mean. All right? Now, if you're sure that limit x goes to infinity, f of x, some concept that you learned from last semester, right? Then, what am I going to write? What do you think I'm going to write? N goes to infinity, an is equal to what? L. Isn't that convincing? I mean, what do you mean by limit f of x is L? I mean, I'm sorry? F of x. Because this is a function, this x can be any is not necessarily integer, right? So what this means is that when x, x varies continuously, when x goes to infinity, for example, if you have a situation, let me show you an example to see what it's trying to say. If I say, for example, f of x, okay, very simple example, 2 over 1, 1 plus 1 over x. Then if I have this, what do you think limits x goes to infinity, f of x is? 2. Right? So, if I build a sequence, so if an, or so, maybe I just say, if limit n goes to infinity, then I just use this formula, which you can put input any x, positive real number, but I input what? N, right? Integer. So 2 over 1 plus 1 over n, what is that? Must be the same limit too. That's because if you look at the curve of f, it settles down to a certain level, certain height. That's what limit. What height? 2. Height 2. Right? But given the fact that all the dots live on that curve anyway, so if the curve itself settles down to the height 2, then of course those dots settle to the same height. Right? That's quite obvious. Okay. Now, you would say that, well, what's the use of this? I don't need that. I just look at this one. Why should I look at this, right? Well, here it comes. Here comes a more meaningful example. F of x is equal to x times sine 1 over x. Okay? And at the beginning, you don't even have this. At the beginning, the problem is simply an is equal to n times sine 1 over n. How about that? So what happens when n grows? Yeah, goes to 0. Which one goes to 0? Sine 1 of n goes to 0. But at the same time, n grows. This grows, this drops. Is that right? Then what happened? I don't know. Okay. Now, look. Let's define f of x as x sine 1 over x. And ask yourself, limits x go to infinity, x sine 1 over x is equal to what? Very similar question, is that right? You know, this one is just to focus on the n thing, is that right? Okay. But you have this one. What can you say?
Does it go to 0, or should we use L'Hopital's rule?
Well, this one is equal to the limit. If you call 1 over x as u, when x becomes very big, positive, u, which is the reciprocal of it, approach what? 0 plus. Is that right? Now, sine of 1 of x means sine of u, right? And what is x? 1 over u. Is that right? This? Is that right? Then we haven't used this for a while. L'Hopital. Right? So what is that? Limits u goes to 0 infinity. This is 0 over 0 kind of deal. That's why I can use L'Hopital rule. Right? And then that becomes what? Cosine u over 1, which is therefore what? 1. Of course, you are familiar with the fact that sine over u, when u is very small, it approaches 1 anyway. Right? But if you want to use L'Hopital rule, then, you know, here's a proof. And so therefore, therefore, limits of n goes to infinity, of n sine 1 over n, likewise, will follow suit. It has to be what? 1. You know, just like this. You prove it as a function level. And the sequence is just sort of specializing to, you know, integer input. And so if